Morning, everyone. Welcome to week 10 to 11 of our science and technology subject. And our topic for today is all about nanotechnology and its applications. Now, in this subject, we will be tackling what is nanotechnology, what are the antecedents of nanotechnology, its applications of nanotechnology, the major impacts to society, and lastly, the social issues and concerns brought about by nanotechnology. So at the end of this lesson, you will be able to learn first, discuss the antecedents of nanotechnology. You will be able to enumerate the positive and negative impacts of nanotechnology to society, to cite applications of nanotechnology across different areas, and to identify social issues and concerns surrounding nanotechnology, and lastly, to critique the issue on its costs and benefits to society. Now, to fully understand what is nanotechnology, first, we must be familiarized with some important words and concepts. First, we have the origin of the nanotechnology, which is the word nano. Um, just how small is nano? And what is nanoscience? What is nanotechnology? What are nanomaterials? What is a nanosources? What is a nano device? And then the importance of nanotechnology. Now, nanotechnology comes from the Greek word nano, which means small or dwarf. And a 1 nanometer is equivalent to a billionth of a meter or 10 to the negative 9 meters. So if you compare that to the sizes of a sheet of paper, it's 100,000 nanometer thick. And you compare that to a strand of human DNA, it's 2.5 meters in diameter. And a 1 inch is equivalent to 25,400,000 nanometers. And if you further compare that to a strand of human hair, the size of it would be 80,000 to 100,000 nanometers. Then lastly, if we compare that a marble, no, then 1 meter would be the size of the Earth. So that's how small a 1 nanometer is. So for further view of how small a nano is, these are some examples. No, if you look at it, a molecule of water, its size in nanometer would be zero point 0.1. A glucose molecule would be 1 nanometer in size or length rather. An antibody would be 10 nanometer. A virus is 100 nanometer. A bacteria is 1,000. A cancer cell is 10,000. A period, the period that you wrote using your pen would be 1 million nanometer in size. And then a tennis ball is 100 million nanometer in size. And this next picture shows you how small a nanofiber is. So if you look at this picture, a nanometer is 100,000 the width of a human hair. So if this is the width of the human hair, and this is your nanofiber, so it would need 10,000, 100,000 rather, nanofiber to fully occupy the width of your human hair strand. So that's how small a nanometer is. Now that we have been clarified on how small a nanosmall is, let's proceed to understanding um, the concept or the field of science that deals with studying these nanomaterials, and that is nanoscience. Nanoscience is the study and application of structures and materials that have dimensions at the nanoscale level. Another definition, it states there that it is the understanding of how these materials at the molecular level provide novel properties and physical, chemical, and biological phenomena that have been successfully used in innovative ways in a wide range of industries. So, because of these size, no, very molecular level of size of these materials, they have these properties, whether it's physical, chemical, and biological, that can be utilized in innovative ways, and it's very useful in a wide range of industries. And when these structural materials are made small enough, like say at a nanoscale range, they take on interesting and useful properties, no? And one of those properties is the strength of that material. It could be tensile, very tensile material, no? Another one is the weight or the mass. So at a molecular level or a nanoscale range, no? Your material could be lightweight. So when you compare these materials to a steel, now you would utilize the material that is more lightweight compared to a steel. So that's one property of a nanomaterial. Another one is the control of light spectrum as well. And then we also have chemical reactivity. So at a nanoscale, it might enhance the chemical reactivity of a certain material. And then even the boiling and melting point, no? Then last, we also have density. So, and lastly, the color. So one example in terms of color is an opaque material could become transparent, no? An insoluble substance could become soluble, and then even the color of gold can be changed to violet, red, and even more. So if nanoscience is the field of science that deals with the study of nanomaterials, then nanotechnology is just the application of nanoscience. No? The science and technology of objects at the nanoscale level and the properties of which differ significantly from their constituent material at the macroscopic or even microscopic scale. So it is a multidisciplinary field that encompasses understanding and control of matter at about 1 to 100 nanometers, leading to the development of innovative and revolutionary applications. When you say multidisciplinary, it deals with different fields. So studying of a certain material that is 1 to 100 nanometer in sizes, it could also involve physics, chemistry, no, astrophysics, or any other fields of science, no, that somehow can be applied to a certain material that is 1 to 100 nanometer in size. So it covers all types of research and technologies that deal with special properties of matter on atomic, molecular, and supramolecular scale. And this study, this nanotechnology also involves design, characterization, production, and application of structures, devices, and systems by controlling shapes and sizes at the nanometer scale. So as I was saying a while ago, nanotechnology involves a lot of different fields of sciences, and that's why it's called convergent. So it brings together various fields of science through its innovations. So one example is um, DNA silicon chips. So you can manipulate DNA using nanomaterial like these silicon chips. Another one is converging with semiconductor science. And we all know semiconductor science involves in inorganic chemistry as well. It could also involve biology, especially on the treatment of diseases. No? So biotechnology as well, and even in the medical industry. And that's why in this conceptual framework, you can see that nanotechnology involves a lot of fields of science. You have information technology, medicine, environment, household, industry, and even energy. It also nanotechnology is also enabling. No? It provides platform and tools to produce innovation. So it is a platform for many scientists, especially those that are involved in nanotechnology, to invent and even innovate devices that could potentially help in these different fields. And the father of nanotechnology is Richard Friedman.
Now, the subject of focus for the study of nanotechnology is nanomaterial. And nanomaterials are materials that are used to create displays that have better color, lower energy consumption, and longer service of life. So these are the very important properties that these materials should have. And nanomaterials can be manufactured and used at a very small scale, 1 to 100 nanometers in size. And they are able to develop and exhibit novel characteristics compared to the same material without nanoscale features like increased strength, chemical reactivity, or conductivity. So, for example, a steel, when compared to an an alternative nanomaterial, that alternative nanomaterial would have more better strength, better chemical reactivity, and conductivity. Now, so what are the examples of nanomaterials? It could be a carbon nanotube. Now, a carbon nanotube um, is a cylindrical, large molecule consisting of large hexagonal arrangement of hybridized carbon atoms. Now, what are the uses mainly for carbon nanotubes? We have um, they can be used as a aircraft and spacecraft body. They could also be used as a bulletproof jacket. Some nanotubes can build high-performance nanoscaled thin film transistors to replace silicon-based transistors as well. We also have diamonds, no? Nanomaterials that are kind of exhibiting diamond diamond nanostructures are utilized in a variety of applications such as energy storage, catalysis, electroanalysis, tribology, lubrication, chromatography, and mass spectrometry. So imaging as well. In addition, one of the sectors where um, nanomaterial diamonds are widely utilized is biology and medicine due to its extremely high biocompatibility. So it's very compatible to kanang application in biomedical um, treatments in biology and medicine. We also have quantum dots. No, quantum dots. Quantum dots are man-made nanocrystals that can transport electrons. So the most commonly known use of quantum dots is your present in your TVs, no? The OLED TVs of Samsung and LG. So those are materials out of quantum dots. Now, quantum dots can also be used in photovoltaics, no, or energy storage as well. Quantum dots enable researchers to study cell processes at the level of a single molecule and may significantly improve the diagnosis and treatment of diseases such as cancer. So it's also keep uh, a material that is helpful in medicine and biology. Quantum dots are either used as active sensor elements in high-resolution cellular imaging as well. No? So, as I said a while ago, chromatography, no, and image processing. Next, we have um, fullerenes. No, the fullerenes are used in medical field it's a light activated antimicrobial agent, so it is used in several biomedical applications. No, it could be applied on the design of high performance MRI contrast agents, X-ray imaging contrast agent, photodynamic therapy, drug and gene delivery as well. So next we have graphite. No, one common example of graphite is the one that can be found on our pencil. No, now graphite is a type of crystal carbon and half metal, along with being one of the renowned carbon allotropes. In the modern times, graphite is usually consumed in steel making, brake linings, lubricants, foundry facing, batteries, to name a few. And one of the important components of graphite is graphene. No, graphene is a certain special feature, and is one of the widely known strong materials. No, it's comparable to even diamond, the strongest and um, most tactile elements that can be found on the planet naturally. To separate the component of a graphene, no, from the carbon crystal would require better advances in technology. So the use of the crystal include electrodes and refractories used in application for processing materials in high temperature. So how does this graphene is um, artificially uh, um, created, no? The first time graphene was artificially produced by scientists literally took a piece of graphite and dissected its layer by layer until one single layer remained. So this graphene, no, it has an amazing property and as the lightest and strongest material compared with its ability to conduct heat and electricity better than anything else means that it can be integrated in a number of applications. So that's why it's very hard to produce artificially a graphene. No? You would have to, as I was saying a while ago, no? You have to let's say dissect it layer by layer until one single layer remains, no, out of the graphite, no, because graphene comes from graphite, no. The graphite was being dissected layer by layer until only one single layer remained. Now the applications of graphene is can be included in biological engineering, no, like bioelectric sensory devices with the ability to monitor such things as glucose levels, hemoglobin levels, cholesterol, and even DNA sequencing. Now, for optical electronics, no, when you say optical, ng imagery, used on commercial scale is that in optoelectronics, specifically touch screens like liquid crystal displays and organic light emitting diodes or OLEDs, no, the one that can be found in your TVs, in your smartphones. And next to graphene is dendrimers, no? We'll not tackle graphene oxide any longer because these are mostly associated with each other. Dendrimers are a new class of polymeric materials, no? They are highly branched monodisperse macromolecules. Its structural advantage allowed dendrimers to play an important role in the field of nanotechnology, pharmaceutical, and even medicinal um, chemistry. One of the products that can produce out of dendrimers, we have adhesives and coatings. Also chemical sensors, also medical diagnostics, drug delivery systems, high performance polymers, catalysts, building blocks of supermolecules, separation agents, and many, many more. Now, next to dendrimers, we have liposomes as well. Now, liposomes are small artificial vesicles of spherical shape that can be created from cholesterol and natural non-toxic phospholipids. Due to their size and hydrophobic and hydrophilic character, no, besides being highly biocompatible, liposomes are promising systems for drug delivery. Next is DNA. Now, DNA nanotechnology uses DNA material, no, to self-assemble, design nanostructures including DNA 2D arrays, 3D nanostructures, DNA nanotubes, and DNA nanomechanical devices, which shows great promise in biomedical applications. No? Various DNA nanostructures have been used for protein characterization, enzyme assembly, biosensing, um, drug delivery, and biomimetic assemblies. No. So in this review, we'll present recent advances of DNA technology and its application in biomedical research field as well. Now, those nanomaterials that I mentioned a while ago can be further classified based on their dimensionality. So, as you can see in this picture, no, we have four different types of dimensions for each nanomaterial. For zero-dimensional nanomaterials, we have the quantum dots, we have the fullerenes, and then the gold nanoparticles. So, this is their structural dimension. No? And we also have one-dimensional nanomaterials like metal nanorods and ceramic crystals. We have carbon nanotubes and metallic nanotubes. As I was saying a while ago, no, this is a carbon nanotube is hexagonal structure. And also we also have gold nanowires, polymeric nanofibers, and self-assembled structures. Now, for the two-dimensional nanomaterials, an example for that is a carbon-coated nanoplates, a graphene sheet, a layered nanomaterial. And then lastly, for three-dimensional nanomaterials, we have liposomes, polycrystalline, and dendrimer. Now, if you're wondering where these nanomaterials can be found or originated, no, the sources for these nanomaterials could be natural and could be man-made. No, naturally occurring nanomaterials could be created through volcanic ash or can be found in a volcanic ash, in a forest fire, in an ocean spray, fine sand, and even dust. So they can be created out of wind erosion and weathering, volcanic activity like volcanic explosion, and even cosmic dust as well. So those cosmic dust that enters the planet when a meteor or a meteorite enters the atmosphere, no? It could also be abiotic and bio-assisted, no, through biotic processes, and also by biomass combustion. So that's how nanomaterials can be produced naturally. Now, nanomaterials could also be created incidentally or anthropogenically as well. No? They are produced as a consequence of human activities like, say, burning of fossil fuels, burn when you're driving your car and your engine burns your fuel, no, um nanomaterials could be created out of that. Now, combustion process, as I mentioned a while ago, no, does not only limit to vehicles, no, even in engineering processes and even manufacturing and industrial processes in our factories. So these nanomaterials could be produced out of that anthropogenic activity. And also, as I mentioned a while ago, nanoparticles or nanomaterials can be produced uh, intentionally for a specific purpose. So they can be man-made. So they are made in laboratories. No? So for example, the graphene. A graphene can be artificially made out of graphite. And even the one that I mentioned a while ago, the quantum dots, no, they can be artificially made in a laboratory. Now, these nanomaterials are being used in order to create nano devices that can be applied to different fields now. And this nano device has one overall dimension in the nanoscale or comprising one or more nanoscale components essential to its operation. So it's either this certain device could have one nanomaterial or even more nanomaterials, no, or parts where there is a nanomaterial, that certain part is made of nanomaterial. Like, say for example, this one, it shows a camera working with other nanoparticles to get rid of a disease. So it could be one nanomaterial utilized to create a certain device, and then or a combination of many more devices made out of nanoparticles or nanomaterials. So in medicine, nanoparticles are created for the purpose of interacting with cells and tissues and carrying out very specific tasks like imaging tools or miniature cameras like this one in this picture that is being shown here. So aside from that, no, there are other devices like aside from cameras, we also have photonic, plasmonic, and metamaterial devices. We have biochemical nanosensing devices, 2 to 6, 3 to over 3 to 4 compound optoelectronics and laser devices, electron and nuclear spin devices, energy harvesting systems, microelectromechanical systems, fluidics and microsystems, low-dimensional nanostructures, topological insulator electric and photonic systems, and bioelectronics. Now, why is it that nanotechnology is important? No? It is to improve existing industrial processes, materials, and applications by scaling them down to the nanoscale in order to ultimately fully exploit the unique quantum and surface phenomena that matter exhibits at the nanoscale. And also to improve existing products by creating smaller components and better performance materials at a lower cost. So, because of nanotech products, no, your material could become lighter, stronger, faster, smaller, more durable, and more efficient. But how did nanotechnology started? So together we will explore how it all started. We will visualize a timeline of nanotechnology and then discover the true approaches to nanotechnology. So how it all started? So it started when the ideas and concepts behind nanoscience and nanotechnology was talked to by an American physicist named Richard Feynman in his talk entitled "There's a Plenty of Room at the Bottom" in at an American Physical Society meeting at the California Institute of Technology on December 29, 59. So there, Feynman described a process in which scientists would be able to manipulate and control individual atoms and molecules. After a decade later, a Professor Norio Taniguchi coined the term nanotechnology after decades of exploration of precision machining. Then next, the microscope needed to see things at the nanoscale were invented relatively recently in the early 1980s. And after that, it wasn't until 1981 with the development of the scanning tunneling microscope or STM that could see individual atoms that modern nanotechnology began. And once scientists had the right tools like the scanning tunneling microscope and atomic force microscope, then it began the age of nanotechnology. So as mentioned, one of the important tools that began the age of nanotechnology is the atomic force microscope. So this one in this picture is an example of an atomic force microscope. And through a detector and feedback electronics. Now, this one, as you can see in the sample, is here the sample surface, and we have the cantilever and tip. So once a laser hits your sample surface or cantilever sample surface, no, it emits light that directly goes to the photodiode, and then this is where detection and feedback happens. So a type of scanning probe microscope that was invented in 1982 by scientists working in IBM, no, was first experimentally used in 1986. So its functioning is able by three of its major parts. I was saying, no, the surface sensing, detection, and then imaging. So the measured properties or primary rule is the magnetism, height, and friction. Next to the atomic force microscope, we have the scanning tunneling microscope or the STM. So it's a type of microscope used for imaging surfaces at the atomic level. And it was developed in 1981 by inventors Gerd Bennig and Heinrich Rohrer. No? It can distinguish small features smaller than 0.1 nanometer with a 0.01 nanometer depth resolution. So this one. Timeline of how nanotechnology started, no? So as mentioned a while ago, it started with Feynman in 1959, no? So through his book there's a plenty of room at the bottom. Then it was followed then by Taniguchi when he termed the nanotechnology, and then the invention of the scanning tunneling microscope in 1981. So these are some just of the timeline of how technology was it was able to get its kickstart now. So from 1959 until 2005. So this is a timeline of how nanotechnology started. And now we proceed to the two approaches of nanotechnology, and we will start with the top-down approach. So the top-down approach states here that bulk materials are being broken down into smaller and smaller particles. So from a bulk material composed of several atoms, and it is being broken down into smaller parts like this one. So four corner of atom is being um, dissected out of this bulk material, and then after that later on they are being dissected even to smaller parts like this one here. And then the second approach is the bottom-up approach, where nanoparticles are built up an atom molecule at a time. So one atom being built up against another one atom, so it produces two atoms, and then you add another one atom to create three atoms, then you add another one to create four, another one to create five, until such time now that you can build a bulk of uh, matter. So it's the opposite of the top-down approach. The introduction to some of the nanomaterials that are being studied in nanotechnology, I've mentioned some applications of these certain nanomaterials. Now let's proceed to the applications of nanotechnology in the everyday life, in medical robotics, in medicine and pharmaceuticals, in gene therapy, in energy applications, agriculture, food industry, textiles, sports, cosmetics, and defense and security. Now, nanotechnology materials has a lot of everyday uses now, and there's a great certainty or possibility that you will always be encountering these nanotechnology materials. Like say, for example, your clothes might possibly contain nanomaterial, or even your sports equipment while playing tennis. There's a greater possibility that this certain tennis racket contains a certain portion of nanomaterial. So every day in your everyday life, you would always encounter nanotechnology. Like say, for example, in the fields of information technology, that cell phone that you are utilizing, the TVs that you are utilizing, the laptops, the computers that you are utilizing, especially these cunning wirings, no, that in order to for your device to catch up internet connection, no, these fibers, they are made of nanomaterials, so you would always encounter nanotechnology in that portion. On energy as well, the solar cells, the fuel cells, the batteries, and the biofuels that your cars or the uh, transportation you are utilizing, no, some of these um, um, engines or vehicles are utilizing nanomaterials in the field of medicine and even in the consumer goods that you consume. So in your everyday life, nanostructured heat protection is present in your vehicle engines. High temperature superconductors for motors as well, no? That is present in your engines. Nano-optimized fuel cells. You will always encounter that as well. Nanomembrane for separation in power plants. Nanocrystalline magnetic materials for transformers. No? Nanoporous material for hydrogen storage. Lithium-ion batteries for energy storage. Nanostructured wear protection, carbon nanotubes for rotor blades, polymer solar cells, dyes, solar cells, and nanostructured thermoelectric materials. So in your everyday life, no, there are a lot of nanomaterials and nanoparticles that are being utilized or applied, no. And these applications would cut across to different or various fields of science, no. Like say for example in nanobio, nanoparticles or nanomaterials and even nanodevices are being heavily applied on mimicry, diagnostics, tissue engineering, implanting devices, drug delivery, and drug discovery. For metrology, um, structure, composition, kinetics, quality control, forensics as well. So like say for example, in satellite imagery is very important in predicting weather patterns. No? So we would always utilize satellites on the outer space in order to monitor the weather patterns on our planet. And these satellites are heavily made up of nanomaterials. Also have sensors. No? It's for consumers, security, planetary science, even environment, and even on the medical field. So that's how nanomaterials are very applicable to this certain field. For electronics, processors, display, photovoltaics, quantum computing, memory, and photonics. And then for materials, aerospace, defense. No, there are a lot of nanomaterials utilized, like say for example the body of an airplane. No, most of these body are made of nanomaterials, and it should be lightweight and very tactile in strength. Then we for energy, catalysis, automotive, construction, printing and packaging, surface coatings, and even cosmetics or cosmetics consumers. So some nanomaterials can be made for cosmetic products as well. As I was saying a while ago, um, nanotechnology application will cut across different fields of sciences. No? And its application could be utilized in energy storage, no, for batteries, no, lithium-ion batteries. For defense and security, like say, for example, the body parts of an airplane, no? Nanotechnology materials could be applied to that. Metallurgy and materials as well, no? Creating better and more stronger um, metals, no? Nanotechnology could be applied to that as well. Electronics, as I was saying a while ago, um, one of examples of nanomaterial applications electronics includes the LED screen of your cell phones, the LCD screens or the OLED screens of your cell phones, TVs, and laptops. And then for optical engineering and communication, we have satellite imaging or telescope, creation of better and high-tech telescopes for better observation of microbacteria. Then we also have biomedical and drug delivery. So for drug delivery, so in order to cure cancer. And then we also have agriculture and food. So nano applications include gene therapy or the creation of genetically modified organisms, no? So nanotechnology is being a device is being applied to that as well on agriculture and food. For cosmetic and paints, so your cosmetic products could be utilized as well, creation of cosmetic products. And then for biotechnology as well, and even on textile application, like the creation of a bulletproof vest. So that's how very important nanotechnology is to these different fields. On the field of biotechnology, biomedical, and drug delivery, um, biological synthesis of nanoparticles is being heavily utilized now. So these microorganisms and plant tissues are being biologically synthesized or being biocompatible with nanoparticles. And the most applicable area for this biological synthesis of nanoparticle application is antimicrobial, antipathogen, and mosquitocidal uses. No? Then also cosmetics and medical appliances. These one can mga Cs or syringes. And then also on the second most applicable area is on nanosensor detection of biomolecules, no? Like cell labeling and gene delivery. And then the third applications under clinical trial, no? Photoimaging and photothermal therapy, and then magnetically responsive drug delivery where nanoparticles are being introduced to a certain defective organ or tissue, and then through magnetism, no, the drug that is being utilized in order to cure that defective or tissue or organ is being magnetically delivered in your body. And then various types of human cancer as well. Now, nanorobotics have the most useful and variety of applications in the medical field. Some of these fields is the drug delivery for cancer, medical instrumentation, surgery, pharmacokinetics, monitoring of diabetes, and even healthcare. Now, in this picture, you're shown of robots, no, nanorobots, curing employed in the medical field at a cellular level. No? These nanorobots are injected into the patient to perform treatment. And these are some of the important uses and applications of nanomaterials in medicine and pharmaceuticals. Now, say for example, for optical imaging with the use of nanomaterials, your optical imaging device would be highly sensitive, multicolor imaging is possible, and it's activatable as well. So through the process of fluorescence. Then for ultrasound imaging, its advantage is it could be real time and it's on low cost. No? For magnetic resonance imaging, your device would be highly special in resolution and then no tissue penetrating limit as well. For radionuclide imaging, one of its advantages of these nanomaterials is it becomes high sensitive and no tissue penetrating limit as well. In the field of medicine, it could potentially revolutionize the cancer treatment, with the use of magnetism. Nanocrystals can be effective agents for selective targeting and destruction of cancer cells. So this is your cancer cell, and then you have the catheter here where the drug is being transported to, with the aid also of magnetism, the drug can be easily target the specific um, defective tissue or cancer cell. So that's how it could revolutionize medicine. No? Another application of nanotechnology in medicine is on imaging and diagnostics, through the use of nanoplex biomarker detection, which is made up of silica-coated surface in hand Raman scattering. Active metal nanoparticles allow robust, ultra-sensitive, highly multiplex biomarker quantitation in any biological matrix, including blood. On the field of sports, nanotechnology can greatly enhance your sports equipment, like say on its resiliency, on its wear resistance, on its reduced waste, increase hardness, reduce friction, enhance durability, and even enhance strength to weight ratio. On the field of cosmetics, nanotechnology can also help a lot, especially with your cosmetic formulation, as it can help prevent sunburn and carcinoma due to UVB exposure, and it can also prevent or enhance prevention from melanoma and premature aging due to UVA exposure. Now, the nanoscale titanium oxide and zinc oxide particles, which could be utilized no, in your cosmetic formulation, provide broad spectrum of UV protection in transparent formulation. In the field of defense and security, nanotechnology has a lot of applications, such as this one, the body armor. Now, the body armor has been the major focus for military nanotechnology research, and even in a few years time rather, it will be operational. Now, some of those researches include silicon or titanium oxide nanoparticles embedded in epoxy matrix, silicon oxide nanoparticles in a liquid polymer that can harden ballistic impact or its shear thickening fluid, and even iron nanoparticles in inert oil, which hardens on stimulation of electrical pulse or its magnetoheliological fluids. Now, aside from that, no, these are some of the applications of nanotechnology and defense security. It could be on clothing, on biorobots, nanorobots, information, virtual reality systems, nanomedicine, automation, robotics, military platforms, chemical sensing, biological sensing, and nuclear detection. And so, as mentioned a while ago, one of the most heavily utilized nanomaterial is carbon nanotubes, and it's a 4 nanometer width nanomaterial which has a smaller diameter than DNA, and it is 100 times stronger than steel, and it's thermally, electrically conductive, and even metallic and semiconductive. So a single walled nanocarbon tube, a carbon nanotubes, is made up of is what we call a graphene chip, while rolled up is a multi-walled carbon nanotube. So, what are the applications of carbon nanotubes? It includes thermal dissipation, electromagnetic shielding, um, applications on your cell phones, laptops, and LEDs, especially its screen. Other applications includes the utilization of titanium oxide nanocrystal films, which is useful in photocatalytic reactions that can purify water, air, surface, and fabrics, and also utilization of nanoscale aluminum powder, which has higher burn rates, and it's mainly utilized now for as a propellant for solid rocket boosters of the space shuttle. Other utilization includes magnetic recording tapes, no? So nanomaterials are also important components in your audio cassettes, video cassettes, data storage tapes, floppy disks, hard disks, and the use of ferrous oxide or iron oxide um, as well. And then for transparent conductive coating, indium tin oxide is utilized on that, and it can be found on your cathode ray tubes, photographic films, and even touch screens. And although nanotechnology has very important contribution to our society, we need to also examine its major impacts, whether it's positive or negative, or what are the advantages and its disadvantages as well. So let's start with the positive impacts of nanotechnology. First is that nanotech products will be smaller, cheaper, lighter, more functional, and easier to use, and it requires less energy and fewer raw materials to manufacture. Second, It increased manufacturing production of products at significantly reduced cost. Third, it allows for more accurate and fast delivery of services. It also, at a molecular scale manufacturing, ensures that very little raw materials is wasted and better performance of products compared to those made with conventional materials. So those are some of the positive impacts of nanotechnology. Now let's proceed to the negative impacts. First is toxicity risk to human health and the environment. So it's associated with first generation of nanomaterials. And second is pulmonary diseases due to inhalation of airborne particles and nanofibers. Since these materials are very small and it's in nanoscale, it's very prone to wind um, dispersion. So it could be led to pulmonary diseases as well. So carbon nanotubes are as harmful as asbestos when inhaled in sufficient amounts. So remember that. Third is when toxic waste from nanoparticles are flushed into our waters become endangered. Now, how about its advantages and disadvantages? We proceed to the advantages first. So it promotes renewable energy, especially on solar energy. So through the utilization of nanomaterials, because of its very efficient utilization of solar energy, no, panels can become cheaper and more efficient. It also extends the limits of electronics. So unlike silicon microchips, nanochips will make it possible to build very precise circuits at an atomic level as well. And then it also allows a more effective medicine. So arteries can be unblocked, cells can be selectively attacked, damaged genes can be repaired, and faster and more precise surgeries can be performed. So that's how, those are some of the advantages of nanotechnology. What about its disadvantages? So it threatens the environment, no? This type of technology could cause negative effects on the environment by generating new toxins and pollutants. So this one is one of its advantages as well. No? It has an impact on the job market as well. The obsolete materials and changes in production processes could destroy jobs, but this technology could create others. And then lastly, it compromises the safety because the properties of this technology could facilitate espionage, the production of new nano weapons, and smart bullets as well. Also, social issues and concerns can also be generated through because of nanotechnology, no? Especially on the ethical aspect and even on the social and legal influences as well. So, what are some of the health issues, societal issues, and futuristic issues brought upon by nanotechnology? First, for health issues, we have the cost of nano devices and nanosurgery tools and the unknown technical capacity of these devices and tools. Second is the effect on the relationship between physician and patient. And then third, the effect on the health system. Now, for societal issues is what is the effect of this technology on developing countries? Since most of these developing countries are not adapted yet to this certain type of technology, so it could greatly affect the job of people there who are kanang utilizing old or conventional materials instead of nanomaterials, no? So they could lose their job on that part. Then getting the rules of the process cycle of nanotechnology, that's one issue as well. The change in the need for raw materials. As I mentioned a while ago, when there is a change in the need for raw materials, it could deeply impact the developing countries because they are the ones who are only utilizing conventional ones, not the nanomaterial one. And then the effect on laborers as well. So that's another issue. Undetermined employee security. Again, that's because there is a need for raw materials. Thus, that certain industry would need people who are skilled on nanotechnology, not the people that are only skilled on in terms of conventional raw materials to be processed. And then unprescribed dangers resulting from nanoproducts, and then the effect on managerial issues. Lastly, for futuristic issues, no, in large expectations and substantial estimations, and there are possible risks brought upon by nanotechnology as well. No, clinical applications of nanotechnological processes, or this could be a futuristic issue as well. The problem of confidentiality, as mentioned a while ago, espionage could be a concern as well. No, the problem of equality and even the problem of definition of being human. On the ethical influences, no, there are issues on ethical influence, like say for example, social divides. If the rich countries are the main drivers of development of nanotechnology and um, applications which benefit developing nations will be sidelined. So, katong mga conventional applications that is only utilized in developing nations will be sidelined in favor of nanotechnology. Technology abuse as well, no? The gray goo, tiny robots generated with nanotechnology could acquire the ability to self-replicate. And then nanotechnology has the potential for revolutionary advancements in military power, a threat when it falls on the wrong hands. So, um, certain people or even in the rich developed countries might utilize, no, their knowledge on nanotechnology for greater advancements of their multi power, and this could lead to abuse, no, to the developing countries, for the poor countries as well. Now, on the social influence, we have issues on environmental hazards, no? Nanoparticles have the potential to remain and accumulate in the environment. It's very minute, very small. It's even smaller than a DNA. Um, it could its shelf life on the environment would take much longer, so it will be harder to clean up these pollutants, these future pollutants in the environment in the future. And then water resources become endangered when toxic waste are flushed into our waters. No, we are even having a hard time with the microplastics pollution problem. How much more if we are um, already experiencing pollution problems out of these nanomaterials. And then health risk. One of the health risks is nanoparticles could have unforeseen impacts on human health. And then nanoparticles could accumulate in the food chain as well. Also, we have economic effects and educational avenues that kanang nanotechnology could also greatly affect. On the legal influence, we have privacy breach, as I mentioned a while ago, no? When it comes to espionage. No? Regulations, unless rapid action is taken, research in nanotechnology will progress faster than a place to regulate its applications and their uses. And then the public has not been sufficiently involved in debates on the application uses of nanotechnology and even property rights. So these are some of the issues, no, that might arise out of nanotechnology, that might or has also already risen from this nanotechnology. So that ends our lecture for today, and I hope you were able to learn something out of this topic. Thank you and good day.